Hello, I'm Lucrezia Ravera, and I will present an action principle for the Einstein-Ball equations, which is based on a work in collaboration with Silke Clem. A long-standing open problem in theoretical physics since 1918 has been that of finding an action principle for the Einstein-Ball equations with non-exact Weyl vector. Here I will present for the first time such an action principle in three space-time dimensions, and as we will see, the Weyl vector will have a non-trivial dynamics. To this aim, we will consider an action given by metric affine FR gravity, plus additional terms involving Lagrange multipliers and Chern-Simons gravitational contributions. Let me start from the state of the art. In 1918, a remarkable generalization of Riemannian geometry was proposed by Weyl in an attempt of unifying electromagnetism with gravity geometrically. In particular, Weyl introduced a connection involving, besides the Levi-Civita part, also the non-metricity tensor that is defined in this way, where this is the covariant derivative with respect to the Weyl connection. Weyl non-metricity can be written in this way, in d dimensions, where the trace part of Weyl non-metricity is called the Weyl vector. In this context, the open problem that we solve is that of finding an action principle for the Einstein-Weyl equations, the latter describing Einstein-Weyl manifolds, with non-exact Weyl vector. These are the Einstein-Weyl equations in the dimensions, and we will focus on d equal 3. Before moving to our results, let me review the theoretical background starting from metric affine geometry. The generic decomposition of a general affine connection can be written in this way, where these are the Christoffel symbols, and where this is the distortion tensor written in terms of the non-metricity and of the torsion tensor. Then one can decompose the non-metricity and the torsion in a trace and a traceless part in this way. This is the decomposition in 3 dimensions, where we have the Weyl vector, another trace of the non-metricity tensor, another non-metricity vector, then the trace part of the torsion, and 2 traceless tensors. Then we can also define the Riemann tensor, the Ricci tensor, and the scalar curvature of the general affine connection. Moreover, when Weyl non-metricity is present, we can also define the homothetic curvature tensor, which is written in this way, in terms of the Weyl vector. Let me spend some words also on metric affine FR gravity. Thus, we consider this action, which is purely gravitational. This is the gravitational coupling constant, and this is a function of the scalar curvature to be specified later. We work in the first order formalism, that is, the metric and the connection are considered as independent variables. From the variation with respect to the inverse metric of this action, we get these equations, and taking the trace, we are left with this one, which is identically satisfied for this choice on F, where C is an arbitrary integration constant. With this particular choice on F, we also have that the action is invariant under conformal transformations of the metric tensor. Then, substituting back this into these equations, we get these equations, which in the case of vanishing torsion and non-vanishing Weyl non-metricity, coincide with the Einstein-Weyl equations in 3 dimensions. On the other hand, considering the variation with respect to the general affine connection, we get these equations where we have defined the Palatini tensor, which is written in this way, and taking the lambda mu trace of these equations, we get this identity, and indeed, this trace of the Palatini tensor identically vanishes. Then, taking the other traces of these equations, after some algebraic manipulation, we obtain that the torsion tensor is written in terms of its trace part, that non-metricity coincides with Weyl non-metricity, and introducing this vector called the affine vector, written in terms of the Weyl vector and of the trace of the torsion, we also have this equation. Now, using this choice on F, we get that this equation becomes this one, and then since FR gravity theories and metric affine hypergravity theories are invariant under projective transformations of the general affine connection, we can exploit this invariance to either set the torsion or the nometricity to zero, or to interchange the trace part of the nometricity with the trace part of the torsion. Then, coming back to this equation, we can see that it can be viewed as an partial differential equation for the Weyl vector, and in this case, the Weyl vector will be exact. Now we can present our proposed action, which contain the metric affine for gravity terms, plus additional contributions. This one is a Chern-Simons gravitational term for the Weyl vector. Mu is a parameter that determines the size of the Chern-Simons gravitational terms. And these terms involve the Lagrange multipliers chi and z. And then we have this term that is a Chern-Simons gravitational contribution for the general affine connection. We can observe that the projective invariance of the metric affine for gravity now is broken due to the presence of these new contributions. We can now study the equations of motion of our model, and from the variation with respect to chi and z, we get respectively these equations and these equations. This is telling us that this trace of the nometricity is related to the Weyl vector in this way, and that the torsion vanishes. Then, taking the variation with respect to the general affine connection, we get these equations, where we have the contribution from metric affine for gravity, and the contribution from the Chern-Simons gravitational terms, and then the terms coming from the part involving the Lagrange multipliers. Then we can perform a consistent truncation of the theory, setting the traceless part of the nometricity to zero. And this can be done since the truncated equations of the original Lagrangian coincide with the equations of motion of the truncated Lagrangian. Then, taking these two equations, we get that the nometricity of our model coincides with Weyl nometricity. Writing the Palatini tensor explicitly in terms of the Weyl vector, taking traces and doing some algebraic manipulation, we obtain first of all this equation, which means that the Lagrange multiplier chi vanishes. And then, considering the variation with respect to the inverse metric together with this equation, we get these equations. Taking the trace, we are left with this one, which is identically satisfied for this choice on F. Then, substituting back this equation into these ones, we find the Einstein-Weyl equations in 3 dimensions. And substituting this back into the equations coming from the variation with respect to the general affine connection, we get that the Lagrange multiplier Z is written in this way, and we also get this set of partial differential equations on Q, on the Weyl vector. And here we can see that in our model, the Weyl vector is not exact, and it exhibits a non-trivial dynamics. Then we can conclude that we have presented for the first time an action principle for the Einstein-Weyl equations in 3 space-time dimensions with a non-exact Weyl vector. Here I wish to observe that when one tries to couple metric affine for gravity with matter, considering a matter action that depends also on the general affine connection, a kind of inconsistency arises, since the projective invariance of the theory imposes a constraint on the matter that can be considered. To avoid this, one needs to somehow break the projective invariance. And this is exactly what happened in our model. Indeed, if we couple our theory with matter, we get that the new contributions we have introduced break the projective invariance of the theory, and thus consistent matter couplings are allowed. Possible future developments of our model consist in understanding the role of our results in cosmological context and in extending our analysis to higher dimensions. Here you can also find some references. Thank you for your kind attention.